Hello, today we are going to use the Born approximation to find a solution to the scattering problem. So we can apply the Born approximation when we have an incoming wave starting from the infinite with momentum k, and the expression for this plane wave is phi incoming wave equals a constant, a normalization constant times the exponential of I, the dot product between the position x and the vector the momentum k. Now this plane wave is scattered by a potential at the origin. So the potential at the origin will cause a disturbance, and the outcoming wave from the origin can be a very general wave in principle, but the Born approximation will apply when we evaluate points far from the origin, and at these points, if we assume that the potential decays pretty quickly, we can consider it a point-like potential basically. So the resulting wave will propagate like a spherical wave, so it will decay as the modulus of x, and considering that actually the potential can have any shape, the resulting wave can have any shape, so the amplitude, it is not spherical actually, and the amplitude will depend on the direction, could have any form, so we have a function which depends on the direction, this is the versa x, the modulus of x equals 1, and here we have the exponential of the spherical wave, which is I modulus of k modulus of x, and our normalization constant. So this is the incoming plane wave, this is the outcoming wave, and our wave in the point x will be the superposition of the two, so phi in plus phi out. Now this expression here is pretty disappointing. Why? Because this is a wave which propagates with the Schrödinger equation, and if we know the potential energy U of x, solving the Schrödinger equation, we should be able to obtain an expression for phi. So we can do better, and we can actually determine what this term will be by solving the Schrödinger equation. The Schrödinger equation, the time-independent Schrödinger equation can be written like this. Here we have the rescaled potential energy U of x equals 2m divided by h bar squared U, big U of x, and here we have k squared phi. Now if we take this term to the right, we get h phi equals u phi, where h is the Laplacian plus k squared. It is called the Helmholtz operator. Helmholtz. And this equation has a homogeneous counterpart, which is h phi equals 0, and this is the Helmholtz equation, a very well-known and studied equation from optics. And the solutions to this equation are the plane waves. And it makes sense because we know that the solutions to the Schrödinger equation, when there is no potential, are the free particles, and we know that the free particles are plane waves. And to find a solution, an expression for phi solution to this equation, we call this phi 0, the solution to the homogeneous equation. We have in between them a similar equation, a bit more complete than this one, but not quite as this one, and it is the green equation, hg equals delta. Now it is usually written for g of x minus x0 equals delta of x minus x0. the solutions to this equation are called green functions, and delta is the Dirac delta, so this is 0 everywhere except at x equals x0, where it is infinite. But if you integrate and do the convolution with another function, it becomes a finite quantity. And the idea is that we can find an expression for phi by combining these terms under an integral. In fact, we can guess that if we have a function phi of the form integral of gu phi, then if we put this function in the Schrödinger equation, we get the integral of hgu phi, and then hg is the delta function, so this function here is u of x times, sorry, this integral here is u of x times phi of x. So we recovered the Schrödinger equation, so this function here satisfies the Schrödinger equation, and in particular we can add any solution to the homogeneous Helmholtz equation, because when we apply h here we get 0, so this does not affect this result here, and so this is a solution to the Schrödinger equation. Now, since we are going to do an approximation, it's really useful to write the solution as a homogeneous solution, which is the free particle solution plus a perturbation term, which is due to the potential U. Now, if I write out the variables so you don't get confused, and also the variable of integration, which is the whole space, this is written as g of x minus x prime u of x prime phi of x prime, and then we add phi 0 of x. So phi 0 of x is clearly this, the plane wave, and this term is going to be this one. Now, the green functions are very well studied functions, so we know expressions for the green functions, and the expression we are going to use, which is a green function, so a function which satisfies the green equation hg equals delta. We can use this expression for a green function of x minus x0, which is minus divided by 4 pi the modulus of x minus x0 times the exponential of I k modulus of k times the modulus of x minus x0. So this is the green function relative to the Helmholtz operator with momentum k. So our perturbation integral will be minus divided by 4 pi the integral of the modulus of x minus x prime exponential of I modulus of k modulus of x minus x prime times u of x prime phi of x prime integrated in the volume x prime. Now we can do the substitution. U is the scaled potential energy to m divided by h bar squared times U, and so here we get 2, here we get m, and we get also an h bar squared. So we found this expression for our solution. By the way, this is not an analytical solution to the Schrödinger equation. That would be fantastic. Unfortunately, this is not the case. This is because in the right hand side we still have our wave function to determine. So we have our solution in the right hand side and we didn't isolate the solution, so this is not solved analytically. By the way, this is a useful expression for the Born approximation, which allows us to find an analytical expression for the approximated solution. So the Born approximation considers the perturbation term to be a small perturbation of the original incoming wave. So this term here is actually much smaller than this one, and so when we put all this term inside this term here, we can approximate this term just to this one. So we write out the whole expression because we are concerned, we are interested in evaluating this term. But when we put this expression inside the integral, here we can cut this part and we substitute this with phi zero. So here we have an exponential term in the integral. Instead of phi zero we have I k dot product x. And make sure to put x prime and not x, because inside the integral phi 0 is evaluated at x prime, obviously. And now we have written here our perturbation integral. So our perturbation term must be equal to this one, and so we can find an expression for f of x. Now there's a problem that we have here the modulus of x, and here we have the modulus of x minus x prime, and same thing here, but we can do approximations because we are considering points far from the origin. So this one approximates to x, modulus of x, and can be brought out of the integral. And then we will do an approximation here to get the modulus of x. So we will now approximate x minus x prime. Now the modulus is the square root of the vector by itself, so this can be written as this multiplying the square root of 1 minus, here we have the double product divided by this factor which we have brought out. So it is here we had x times x prime, now we are dividing by this squared, so we use here divisor x, and here we have plus x prime divided by modulus of x all squared. Now we want to approximate for this ratio to be very small because we are very far from the origin, and the points x prime are close to the origin, remember, because these are the points where we are evaluating the integral, and the integral contains this potential term which is 0 far from the origin, because by hypothesis it decays very quickly, so the x prime are all close to the origin. So when you do the approximation x minus x prime far from the origin, it will approximate here with modulus of x, and here with the approximation which we are doing now for this ratio being very small, and we call this ratio y, and So this is the modulus of x times f, where the function, I don't want to confuse it with this one, I will call it g or y, where g is the square root of 1 minus 2 the value of the product. This dot product here can be written as the modulus of x prime times the cosine between x and x prime. So this is minus 2 cosine times y plus y squared. Now I need some more space here. So g prime, we are going to do the Taylor series approximation, so we evaluate g prime, which is 1 divided by g and 2 minus 2 cosine plus 2y, but the 2 here cancels out, so this is g prime, and we have g0 equals 1 and g prime of 0 equals minus cosine, so g is about 1 minus y cosine. And so this is about the modulus of x times 1 minus y cosine, and the y is the ratio I had written before, so multiplied by the modulus of x, it is x prime, and then we have the cosine, so we can write this as x prime times dot product the value x. So this is an approximation for this, which we can substitute here and get this modulus, which we cancel out with this one here. So let's write it here, and we have times modulus of x minus x prime times the value x. So now this term here, we go outside the integral and it will simplify with this one here, and this term simplifies with this one, so we are left in the left hand side only with f of the direction, and it is minus n divided by 2 pi h bar squared, the integral in the cube of x prime times the exponential of, and now inside the exponential we have I times modulus of k times minus x product x prime product x value plus, oh sorry, here we had a prime, I k times x prime, and we can write this as I times x prime modulus of k times minus value x plus plus value k. So we put it inside here, and we have I times x prime vector dot product q, where q is defined as this modulus of k times value k minus value x, and then we multiply by the potential. Sorry, this is not anymore risky potential, we are using now the actual potential. And I forgot to write here big U instead of small u when we did the substitution from u to small u to big U. and so obviously here there should be big U. Now the Born approximation is mostly used when you have a central potential, because in that case we can find a very simplified form for this integral. And so now we integrate in spherical coordinates, so this becomes r squared sine of theta dr d theta 2 pi, because phi is not contained in the integral, because now this term here we can write it as like this, k minus x. Now let theta be the angle between k and x, between these two, versus if we take the modulus of q, the modulus of q is k, the modulus of k times the modulus of this, which is the square root of the product, the dot product with itself, which gives 1 plus 1, which is 2, minus the double product 2 times the dot product between these, which is the cosine of theta. So we have this expression for the modulus of q. Now we can write it in terms of the sine of theta half, because cosine of theta is 1 minus 2 sine squared of theta half. So this becomes 1 minus cosine of theta equals 2 sine squared. So this divided by 2 is sine squared of theta half. Sorry, we didn't need to divide by 2, because now we substitute here and we get 2 sine squared of theta half, sorry, 4, and this becomes, we call it simply k, so the square root of this is 2k sine of theta half. So we obtained, we call it simply q equals 2k sine of theta half. So now if we choose q to be the z-axis, so that theta is the angle, sorry, call it theta prime so we don't confuse it with this theta here. Theta prime, the angle between q and the vector x, then the dot product q times x prime will be q modulus of x, which is r, times the cosine of theta prime, where q is this quantity here. So this integral here, remembering that now we have a central potential depending on r, and is minus m divided by 2 pi h bar squared times the integral, and here we have, we multiply by 2 pi, we have r squared dr sine of theta d theta, and then we have the exponential of I q r cosine of theta prime, sorry, this is theta prime, and all this is evaluated at q equals 2k sine of theta half. And we have also our potential energy, sorry. So now we're going to do a change of variable, so cosine of theta prime, we call it c, So dx is minus sine of theta prime d theta prime 0 to infinite, and here we have this one here is this with a minus sign, which means that we have 0. We invert the order, so pi here and 0 there, but now we are using dx, so we should put the values for xi. So when theta prime is 0, xi is 1, and when theta prime is pi, xi is minus 1. So we got rid of this term here. Now we have r squared dr exponential of I q r xi u of r. So now we can do the integral in dx. We get minus m divided by h cut squared integral from 0 to infinite of r squared dr, and the integral in dx of this, we also write u of r here. The integral here becomes the exponential of I q r xi divided by I q r evaluated from minus 1 to 1. Then the r squared u of r, this becomes, you substitute 1, then you subtract, but with minus 1, so it becomes 2i sine of qr divided by iqr. So you divide by I and you're left with qr. Then you can simplify here, and you can now simplify, so you can now bring out of the integral with this. So you now have 2m divided by h bar squared q integral from 0 to the infinite of dr r sine of qr u of r. So the scattering amplitude, which is this squared, is 2m divided by h bar, and now we simply square everything. So we have dr, let's write the q out. From 0 to infinite of dr r sine of qr u of r. Simply squared everything at q equals 2k sine of theta half. So to find the total cross section, we do the integral in the solid angle. So it is from 0 to pi of all this thing here squared at q equals 2k sine of theta half. So first we write sine of theta in terms of theta divided by 2, and so this is like sine of 2 theta half, so it is 2 sine of theta half cosine of theta half, and then we see that the differential dq is k cosine of theta half d theta. So this one here with d theta is 2 sine of theta half dq divided by k. Sorry, I have written sigma of theta usually is sigma and does not depend on theta, since we're doing the integration in the theta. So now we can rewrite it as 2 pi to m divided by h bar squared, and now we have the integral from, now we are integrating dq, so it is from 0 to sine of pi half is 1, so from 0 to 2k, or 2 sine of theta half divided by k in dq, and this one here is q divided by k, and so we arrive at this expression here times the, or this thing here squared. And I forgot to add the 1 divided by q squared that was outside the integral, so we arrive here. Now we found the right expression, and in particular this is usually written in this form here: sigma k equals 2m divided by h bar squared. So take this term here, then we have an 8 pi here, so we must divide by 4, and in fact we then take out 4 and k, and we get a 4k squared here, and finally the integral from 0 to 2k of dq divided by q, and then this integral here squared, which was I write it here, integral from 0 to infinite of r sine of qr u of r and dr. So these are, in summary, the results we obtained. This is the differential cross-section that now I have written in function of I of q. I of q is this integral, so you first compute this integral, and then you know the differential cross-section by putting q equals 2k sine of theta half. Then you have the total cross-section that I have written in function of this integral j, which is this integral that you can compute once you know this integral. So by computing these two integrals, you know the total cross-section. So this was all for today. See you next time. It has been a pleasure.